Welcome to The Explainer. Today, we're diving into Math Magic Revealed, the algebra behind the shortcuts. You know, we've all been handed those math tricks that feel, well, basically like magic. But today, we are stripping away the illusion and looking right at the engine underneath.
Let's kick things off with this really cool number play experiment from our source material, set up by a student named Anshu. The challenge? Take 4 consecutive numbers, think 3, 4, 5, and 6, and just randomly toss a plus or a minus sign between them. You can try this yourself with literally any 4 consecutive numbers. The burning question here is, can you arrange those pluses and minuses in a way that actually results in an odd number?
So if you sit down and systematically list out the different combinations, you're hit with this totally wild pattern. Just look at these results. 18, 6, 8, -12, +12, -16. It doesn't matter how you jumble up the addition and subtraction. Literally every single result, even the negative ones, is an even number.
Check if anyone got an odd number. Why didn't you? It really feels like a magic trick, right? Ask around. Check if anyone you know managed to get an odd number doing this. Spoiler alert, they didn't. But why didn't you? Is there a way to figure out why this pattern holds up using actual mathematical reasoning, instead of just exhaustively testing numbers until the end of time?
Well, this is where algebra swoops in like a decoder ring. Let's walk through these steps. Step 1, start with the expression a plus b minus c minus d. We're just swapping those specific numbers for letters here. Now, step 2, switch that plus b to a minus b to get a minus b minus c minus d. If you subtract the new expression from the old one, the a, c, and d just cancel right out. And step 3 shows us the difference between them is exactly 2b. And hey, since any number multiplied by 2 is definitely even, switching a sign just changes your overall result by an even number.
If the difference between two numbers is even, they must have the same parity. That is the undeniable algebraic truth right there. Same parity just means they're either both odd or both even. Since the difference is always an even number, like our 2b, the parity never actually flips. This mathematically proves that once your initial sum is even, your final result is locked in as an even number, no matter how many times you swap those signs around. Learning maths is not just about knowing some shortcuts and following procedures, but about understanding why something works. I love this quote from our source text because it perfectly captures our core philosophy today. Math isn't just about endlessly memorizing flashcards. It's a massive playground of logic. It trains your brain to hunt for structural truths, showing us that every single shortcut has a deep underlying explanation just waiting to be uncovered. Divisibility shortcuts for 2, 5, and 10 rely entirely on checking the units digit. We've all used these, right? If a number ends in a 0, boom, it's divisible by 10. Super simple. But the rules for 9 and 11, those are much deeper mysteries. They actually force us to look way past that final digit and dig into the very structure of our number system itself.
Why does the sum of the digits rule work for the number 9? I mean, back in grade school, we were all taught to just add the digits together, and if that sum is divisible by 9, the whole number is. But stop and really think about that for a second. Why on earth does adding individual digits across completely different place values somehow guarantee it's a multiple of 9?
Standard base 10 number, 100. Algebraic secret identity, 99 plus 1. The crucial trick here is splitting our standard base 10 numbers into their algebraic secret identities. We're basically separating out the biggest possible multiple of 9. So, instead of a plain old 100, think of it algebraically as 99 plus 1. 10 becomes 9 plus 1. 1,000 becomes 999 plus 1.
Do you see the pattern here? Whenever you divide powers of 10 by 9, you always get these perfectly grouped multiples of 9, leaving behind a stubborn remainder of exactly 1. Every single place value, whether it's the tens, the hundreds, or the thousands, is literally just a multiple of 9 plus 1.
Let's see this in action by expanding 7309 algebraically. 7,000 is really 7 times 999 plus 1. 300 is 3 times 99 plus 1. So the number is basically just this giant pile of 9 multiples that divide perfectly, plus those single remainders multiplied by the actual digits of our number. 7 plus 3 plus 0 plus 9.
The remainder of 7309. 7 plus 3 plus 0 plus 9 equals 19. Then 1 plus 9 equals 10.
then 1 plus 0 equals 1. Because those massive multiples of 9 are already perfectly divisible, we can just completely ignore them. We only care about the leftovers. We just keep adding those leftover digits together. 7 plus 3 plus 0 plus 9 gives us 19. Repeat it for 19. 1 plus 9 is 10. Repeat it for 10. 1 plus 0 is 1. We've just mathematically guaranteed our final remainder for 7309 divided by 9 is exactly 1. No long division required.
The shortcut to find divisibility by 3 is similar to the method for 9. And honestly, since all multiples of 9 are inherently multiples of 3 anyway, this exact same remainder logic flawlessly explains the shortcut for divisibility by 3 too. Any power of 10 is just a multiple of 3 plus a remainder of 1. The mechanics are absolutely identical, which is exactly why that sum of the digits trick works like a charm for both numbers.
How do we crack the mysterious alternating rule for 11? Okay, let's dive into the trickiest one. The rule for 11 is notoriously weird. To check for divisibility, you're supposed to add up the digits in the odd positions, add up the digits in the even positions, and then subtract them. Seriously, how do we use algebra to make sense of this bizarre alternating digit rule?
Let's take a look at place value, multiples of 11, and remainders. We're going back to our place values, but this time focusing on how they interact with 11. Unlike 9, the powers of 10 aren't always just one more than a multiple of 11. They mathematically alternate between being one more and one less. The units place, 1, is 1 more than 0, but the tens place, 10, is 1 less than 11. The hundreds place, 100, is 1 more than 99. 1 is 1 more than 0. 10 is 1 less than 11. 100 is 1 more than 99. Every single time we move to the left to a new place value, that remaining digit flips. It alternates right between a positive 1 remainder and a negative 1 remainder. Positive 1 for units, negative 1 for tens, positive 1 for hundreds, negative 1 for thousands. It's this perfect built-in oscillation hiding right inside our base 10 number system.
Divisibility by 11. Find the difference between the sum of odd and even place digits. This beautiful alternating pattern of structural remainders is the exact reason why the shortcut for 11 asks us to subtract the even-placed digits from the odd-placed ones. The odd positions carry a positive 1 multiplier, and the even positions carry a negative 1 multiplier. Algebra isn't just explaining the rule to us here. Algebra literally is the rule. Mathematical reasoning lets us skip the endless calculations. Just like that parity worksheet we started off with, using mathematical reasoning lets us completely bypass infinite combinations. We get to uncover these pure logical truths that are constantly operating behind the scenes. When we stop just blindly following rules and actually start investigating the structures, like algebraic equations and place value remainders, we unlock a much deeper and honestly much more satisfying level of understanding.
Group pebbles by 3 or 5, and 1 remains. Group by 7, and perfection is found. How many pebbles are there? Let's wrap up this explainer with a classic mystery straight from the text for you to solve, using your brand new structural math skills. Imagine you've got a pile of pebbles. If you group them by 3, 1 remains. If you group them by 5, 1 remains. But if you group them by 7, perfection is found, 0 remainders. Now the total number of pebbles is less than 100. Using everything we've just talked about regarding multiples and remainders, how many pebbles are there? I'm going to leave you to crack that mathematical code on your own.